Hello. In this video, I will show you the analysis of a Tesla Model 3 motor using MotorXP-PM. Here, I am using the MATLAB version of MotorXP-PM. Open the Geometry Editor tab of Design Studio to start entering motor parameters. To avoid error messages while entering geometry parameters, let's disable the automatic update of the geometry using this checkbox. Open the Stator Editor to enter dimensions of the slot. Each geometry template has a user guide with all of the dimensions shown. Error and warning messages are updated with every change of geometry. Old messages can be deleted using the Clear button. Enter axial geometry parameters. The rotor is imported from a DXF file. Since the drawing shows a full cross-section, the division factor should be applied to select half of the pole pitch. Division factor should be twice the number of poles. Assign materials. Open the Winding Editor tab. The winding has 3 parallel paths, 2 turns per coil, and a 40mm axial overhang. Fill factor is adjusted so that the phase resistance is 4.75 milliohms. Next, open Mesh Editor tab. Some mesh improvements. Now close Design Studio and save the project. It is recommended to create a separate folder for each project so that all of the files related to a single project are stored in one folder. Now let's start no-load magnetostatic analysis, setting up zero current. More points will result in a higher resolution on the waveform plots. Now that the results are ready, which took less than 4 minutes, let's review the back EMF and cogging torque waveforms. To plot line-to-line back EMF, simply subtract one phase value from another. Now let's plot torque calculated by the Maxwell stress tensor method, which is a cogging torque in this case since the current is 0. Use the flux density distribution plot to make sure that the motor is not saturated by magnets. There are also flux density levels in the results panel, which can also be used to assess the flux densities in different parts of the motor. Let's save the no-load simulation data in a separate file and then run the simulation under load. Once any analysis is started, all motor parameters in Design Studio become unavailable for editing. To change motor parameters, the file can be unlocked by clicking the Unlock button. After the file is unlocked, all analysis data will be deleted. Now, let's increase the winding and magnet temperature for the load test. I would like to determine the current required to produce the maximum torque, which is reported to be 430 Newton meters for this motor. My first guess for the current is 800 amperes. Since this is an interior permanent magnet motor, the advance angle corresponding to the peak torque needs to be determined. The fastest way to determine the peak torque at 800 amperes is to use the steady-state DQ analysis plot wizard. Current is 800 amperes. Let's use FEA-based model type so that there is no need to build the DQ model. In this case, the FEA simulations are used to derive the DQ parameters of the motor for each operating point, and then the results are directly determined. Speed can have any value since speed does not affect the torque in this case. Plot versus advanced angle. Let's use advanced angle value in the range from 10 to 80 electrical degrees, with a rough step size of 10 electrical degrees. And click the plot button. Results are ready in about a minute. The peak torque of about 368 Newton meters is observed at an angle of 50 degrees. Now let's run magnetostatic analysis for a current of 800 amperes and advance angle of 50 degrees to determine the torque constant of the motor, and to define the current required to produce maximum torque of 430 Newton meters. I am going to use a single point simulation setup, which is the fastest analysis option. Results are ready in a matter of seconds. Single point simulation is run only for one rotor position, so the rotor rotation is not taken into account. It also does not allow the iron and magnet losses to be determined, so the results are quite rough compared to the simulation setup with multiple points. Single point simulation can be useful when fast results are required, but have a reduced accuracy. I will use torque constant to estimate the current required to produce a torque of 430 Newton meters. The estimated current is 935 amperes. Now let's use the steady state DQ analysis plot wizard again to plot the different torque curves for several current values ranging from 900 to 1000 and advanced angles from 40 to 65 with a step size of 5 degrees. With the new curves available, the new guess for the current is 970 amperes, and the advanced angle range is from 53 to 59 degrees with a step size of 1 degree. The torque value is now very close to 430 Newton meters. Now let's compare this result with the multiple points magnetostatic analysis using the same current and advanced angle values. Note that there is some difference between torque values since multiple points magnetostatic analysis gives more accurate results compared to the DQ analysis. In this case, the torque value is averaged over 144 rotor positions.